We are now moving into our last chapter in calculus, chapter 5 on integrals. And in section 5.1, we're going to talk about area and estimating with finite sums. So in this section, actually, you probably won't see much of a tie-in to what we talked about in section 4.7, integrals. Although you'll see, once we get to the fundamental theorem of calculus, how this all works. So for now, you just need to kind of bear with me and understand what's going on. The problem that people were trying to solve back when they were trying to invent calculus to help them solve this problem is, how do I find the area underneath a function like this? Say we want to find the area that's underneath this function, this region R, let's call it, 1 minus x squared. Well, there was no way without calculus that people could figure out how to find the area of this function. So what they did was, at first, they said, well, let's just approximate this area. Okay, there's no simple formula for it, like an area of a circle or an area of a triangle or something like that. And since we know how to find the areas of rectangles pretty simply, right? Base times height, what they said was, let's kind of methodically use a set number of rectangles to approximate the area. So this is approximating the area of that region. Remember, this is the function 1 minus x squared. We're trying to approximate the areas to region, and they're using two rectangles. So they split the region along the x-axis into two equal length intervals. So you have equal bases for two rectangles. And then in this case, they took the height of the rectangle to be the left corner, the left top corner of each rectangle. Okay, so in other words, if you see the rectangle, the first rectangle is this guy, second rectangle is this guy, and you add up the two areas of these rectangles, and you can see it overshoots the exact area. But if I take more rectangles, let's say I take 4. So now I'm going to break up the interval into 4 intervals. This interval from 0 to 1 on the x-axis, break it up into 4 equal length subintervals to have each one of those be the base of a rectangle. And then I still take the upper left corner here. This is called an upper sum because I'm going over the curve. I'm summing up the area of these 4 rectangles that all 4 of them go over the curve. So I still have some error, but if you can, your eyeball can actually tell you the error here for these 2 rectangles is more than the total error for these 4 rectangles. Okay, so that's called taking the upper sum of them. Some people have said, well, why overshoot it? Let's undershoot it. So instead of taking the left top corner of each rectangle, we're going to take the top right corner. And notice that means this 4th rectangle in this picture here doesn't have any height, so there is no rectangle. But the error here is now undershooting, right? I have area that is actually under that curve that we're not counting. We're only counting the area inside these 3, well, technically 4, but there's no area in that 4th rectangle. Then some people say, well, why overshoot? Always overshoot or always undershoot? And the way we can kind of go half and half, sort of, not quite half and half, but sort of reducing the errors using the midpoint of the rectangle's base as the height, right? Because remember, the area of any rectangle is the length of the base times the height. So anywhere along that base, since the top of the rectangle is the same height, we can use. So this is using the midpoint of each, and you can see some places it undershoots, some places it overshoots. And those errors start to cancel each other out, and you get even a better approximation. Okay, I'm not actually figuring out the area of all these guys, I'm just showing you the idea. And then you can kind of visually see that the more rectangles I take, the better my approximation to the area of the curve is going to be. And I got to sum up the area of 16 rectangles here, or 16 here for undershooting and overshooting. A lower sum and an upper sum. But the idea is that my error goes down with the number of rectangles I take. So that leads us into, and I'm not saying it yet in the notes, but that leads us into the concept of the limit. We're going to want to take the limit as the number of rectangles goes to infinity. Limits, that's what calculus did for us. So we can't really take an infinite number of rectangles, but we can see through some calculus and some algebra that we can take the limit as the number of rectangles goes to infinity and actually get the exact area. That's where we're going to be headed. So that was the end of example 76.